Okay, look at the data from recent examiner reports. Year after year, highly capable physics students walk out of their exam feeling perfectly confident, only to get the results back and find out they've missed the top band by just a handful of marks. They know the formulas, right? They've memorized the flashcards. So, where exactly is the disconnect? Well, welcome to this explainer. Today, we're putting on our data detective hats to uncover exactly where those marks are vanishing, specifically when we're dealing with covalent network solids within crystal structures. Here's the painful reality. Ordinary revision methods are actually setting you up to fail. Cambridge physics students are consistently losing marks because they're memorizing definitions in a total vacuum. They memorize the labels without understanding the physical reality underneath it all. I mean, they picture a flat, two-dimensional diagram from a textbook instead of visualizing a massive, three-dimensional network of vibrating atoms. And listen, if you're just rote learning a sentence without grasping what is physically happening inside the material, the examiner is going to spot that instantly. And that brings us directly to your battleground, the Cambridge International AS and A-Level Physics Syllabus, code 9702. Everything we cover in this explainer is hyper-targeted to this exact syllabus. No generic study advice here, no fluff, just the exact strategy you need to conquer the 9702 mark scheme and secure those top marks. Falling into the trap of unstructured memorization is a massive grade boundary risk. A scattered collection of facts, even if those facts are technically true, will absolutely not secure top-band marks. You have to remember, the examiner is not looking for a trivia list. Physics is all about mechanics and consequences, not just reciting a glossary. They're looking for a disciplined, logical sequence that actually proves you understand fundamental cause and effect. So, let's dive into this. To survive the examiner's pen, you need a rigorous framework. It's a precise four-step process. 1. Clearly define the concept. 2. Provide the evidence or data. 3. Apply scientific reasoning to connect the two. And 4. Package it all up in precise examiner wording. Think of this as building a sturdy bridge from a microscopic atom all the way to a macroscopic machine. This framework is your absolute shield against losing those easy, yet totally elusive explanation marks. Section 1. Application First Physics. Reversing the flow. To truly grasp covalent network solids, we actually need to reverse the usual academic flow. Instead of starting with an abstract definition and slowly working our way down to how it's used, we're going to use an application-first approach. We have to start with reality. Look at the real world. We've got semiconductor wafers in electronics, turbine blades in aerospace, structural alloys and gemstones. By starting from a physical phenomenon and working backward to the microscopic picture, you build actual deep understanding, not just memory. Think about the extreme, blistering heat and the intense mechanical stress a turbine blade has to endure while it's spinning inside a jet engine, thousands of feet in the air. Why does it hold together instead of just melting or shattering? Well, because its crystal arrangement controls its packing, its bonding direction, and its defect tolerance. The macroscopic magic comes entirely from the microscopic structure. Which brings us right to the foundational definition. A covalent network solid is a solid where macroscopic behavior and measurable consequences are interpreted from internal mechanisms at the atomic or carrier level. Notice the contrast there? The massive structural integrity of a turbine blade or the super precise electrical properties of a semiconductor wafer are direct consequences of what is happening internally at the microscopic level. All right, so now you have the definition, but hold on because I'm about to share a vital examiner clue with you, a total secret that changes your exam answer completely. It's a specific structural flow that examiners are actively scanning for when they grade your paper. If you don't use it, you cap your marks immediately. So stick with me here because leaving this explainer right now means you're going to miss the absolute essential link for those top band grades. Okay, so the crucial point is the strict sequence right here. The safest answer structure for the 9702 exam requires moving in this exact order: definition, mechanism, consequence, application. You define the idea, then you describe the microscopic mechanism, you identify the measurable consequence, and finally, you connect that consequence to one real-world material or device. If you can explain those 4 stages in order, you unequivocally prove that you understand cause and effect. Section 2. Spot the error. The examiner's lens. Let's see how this builds in a real exam context. We're going to look through the examiner's lens at a side-by-side analysis of 2 actual exam outputs, and I want you to try and spot the flaw before I point it out. Now, what's really interesting about this contrast is, On the left side, the student states the correct technical term and immediately jumps to a real-world application like a semiconductor. Honestly, it feels like a good answer, right? But it scores terribly. Over on the right, we have a highly disciplined paragraph. It connects the microscopic mechanism, that continuous network of covalent bonds, directly to the observable physical effect like a high melting point or extreme rigidity, before it even mentions the application. The answer on the left committed the fatal error. They stated an application without linking it back to the underlying microscopic reason. They basically handed the examiner a scattered collection of facts instead of a connected mechanism. If you just write down that a diamond is a covalent network solid and it's used in cutting tools, you've missed the middle entirely. You absolutely must explain what physically happens inside the solid to cause that extraordinary hardness. Mechanism to consequence, that is the vital link. A fantastic way to test if you've truly mastered this framework is to compare this microtopic with a nearby idea. Look at this comparison between covalent network solids and simple molecular solids. By mapping out structure, energy, transport, and field response side by side like this, you create clear boundaries in your mind. Examiners absolutely love to test if you confuse related concepts. For instance, just look at the energy row. In a covalent network, you are forced to break massive, strong, continuous covalent bonds to melt it, which means astronomical energy requirements and super high melting points. But in a simple molecular solid, you're merely overcoming weak intermolecular forces, like van der Waals forces, leaving the actual molecules totally intact. That means very little energy and low melting points. Or consider transport. Rigid, localized electrons in a network solid mean it acts as an insulator, compared to potentially mobile carriers if we alter the structure, like we see in graphite. Seeing these clear boundaries prevents you from slipping up and using the wrong microscopic mechanism for the wrong solid. Section 3. The memory triggers. Okay, we're now going to shift gears into a highly interactive rapid-fire checkpoint. Knowing the theory is one thing, but being able to quickly recall it under the intense pressure of an exam clock, that's another entirely. So I'm going to challenge you right now to lock in your retention. Can you genuinely answer the next 4 prompts aloud from memory? Because if you can, your grasp of the physics is definitely secure enough for revision use. All right, here they are. What is it? What changes inside the solid? What can we observe outside the solid? And where does it matter in technology? Notice how answering these 4 simple conversational questions maps perfectly to the strict definition, mechanism, consequence, application exam wording we covered earlier. It's the exact same rigorous framework, just packaged as quick memory cues to trigger your recall when you need it most. Section 4. The next examiner clue. So, you now possess the theoretical framework for covalent network solids. You know exactly how to structure your descriptive answers to avoid those fatal errors and secure top band marks. But we have a very dangerous gap remaining. What happens when the 9702 examiner pivots? You have the theory down, sure, but what happens when they demand linked practical skills and data analysis? What if you're suddenly asked to interpret a tricky graph of specific heat capacities or resistivity data for these materials? Listen, theory without the follow-up data analysis skills will leave you stranded right below that top grade boundary. It's an unresolved problem that you must fix before exam day. So ask yourself, if you can't prove your theory with hard data, do you really understand the physics at all? The next clue to bridging that gap is waiting in our follow-up explainer on data analysis. We're going to take the exact framework you just learned and apply it directly to the rigorous data sets you're actually going to face on the paper. Subscribe to our YouTube channel ACE Exams at acetheexams_IGCS to excel in your Cambridge examinations. Go ahead and click through to that next practical explainer right now, and let's secure those remaining marks.